Hi everyone, I'm Zhang. I'm a fourth year PhD student in Dr. George Rücksak's lab. My presentation today is Algorithmic Fairness in Medicine, a case study in glomerular filtration rate GFR prediction. So most of my talk today will be focused on a case study, the impact of race on GFR prediction. I will show you the background, the study design, the results, and the conclusion. And if time allows, I would like to discuss some of the ideas or my reflection on this case study and what I think that we need to focus on in the future on algorithmic fairness and a potential framework I call it the letter of fairness. So yeah, let's get into it. Risk correction is not common in clinical algorithms. And if you haven't read this paper, I would highly recommend you Hidden in Plain Sight. It was published last year in New England Journal of Medicine. The authors of this paper gave examples of algorithms that use risk correction across a wide range of clinical disciplines, including cardiology, nephrology, oncology, and many, many more. It was very striking to me to see that how many clinical algorithms that use race, although the role that race plays in those algorithms is still not well understood, whether race is a biological construct or it is a social construct or it's a combination of both. I think the medical society still lacks a very good understanding, a good answer to that question. So the appropriate use and the implications of using a variable that encodes a patient's race in medical algorithms remains very unclear. So that paper, I think that shows you, what the big ocean looks like. Now let's look at this one drop of water under a magnifying glass, the CKD epi equation for estimating glomerular filtration rate, abbreviated GFR. It is an indicator of a kidney function. Nephrologists use it to diagnose chronic kidney disease, and it also has many other clinical use. So I have this equation here on the slide, and we can see that it doesn't actually have that many variables. So serum SCR stands for serum creatinine. It is a waste product in the blood, and it has age, it has gender, and it has this race correction factor for people with Black race. And the corrector size is 1.159. So what this means is that for patients with the same serum creatinine level, same age, and same gender, Black patients are estimated to have 1.159 times higher GFR than their white non-Black patients. So, and again, this equation, the use of race in this equation lacks biologically substantiated evidence. So then what is really the impact of this correction factor in a population? There was a paper that answered this question. A group of scientists from Harvard Medical School published earlier this year. They look at the CKD epi equation for estimating GFR. They removed the race modifier that I just showed you, the 1.159, and not surprising that it lowers the eGFR for Black patients with a median change of 14. And how does this impact recommended care for Black patients? They also gave the potential impact on care, and the mostly impacted is CKD diagnosis. So roughly 3.5% of Black patients would have been diagnosed with CKD if the race modifier were not used. And as we go down the list, we can see a lot of other things could also be impacted: reclassification of kidney CKD stage, referral to a nephrologist, and also eligibility for kidney transplant waiting list. I heard some noise from the audience. If you can mute yourself, that would be great. Thank you. So from their studies, I think it's not hard to see that the change of eGFR could have a significant impact on recommended care for Black patients. However, they didn't tell us whether removing the race modifier leads to a more accurate GFR prediction for Black patients. In other words, right, if this change of eGFR really reflected a better prediction of GFR for Black patients, and that is left to be studied. So for our study, we have two research questions. Right? First, does removing race lead to more accurate predictions? And second, does removing race lead to a fair algorithm? And to assess model performance of a prediction model, I think we have many metrics. For binary outcome, we have for accuracy, sensitivity, specificity, precision recall. For a continuous outcome, we can use root mean square error or mean square error. But how to assess the fairness of an algorithm? I think we still need a few tools. And that's why I want to discuss a few definitions of algorithmic fairness that have been proposed in the past several years. This is not a comprehensive list of the different definitions of algorithmic fairness, but I think each of them represents a category of definitions that you can see how they're related. And each of those four have a very distinct mechanism in how they determine fairness. And just to make sure that we are on the same page, I'd like to introduce a few notations. The variable A means a protected or sometimes a sensitive. Think of it as race, gender, age, and in the GFR example, A will be race. Y is an outcome of interest. T is a treatment or intervention. X are some covariates. Y hat is the predicted outcome from a model. And Y parentheses A is a causal quantity that is a potential outcome when we intervene on A. And we will discuss them in the context of the different definitions. So the first definition is called a demographic parity. So here's this a formal definition that a predictor Y hat satisfies demographic parity if Y hat and the protected attribute A are independent. And to show this definition using probability notation, that means the probability of Y hat given A equals A, little a, is the same as probability of Y hat given A equals little a prime. So what does it mean? What does this mathematical equation mean? Let me give you an example. For example, if I were to build a predictor for fever, right? If I want to predict whether someone has fever or not, and if I use this fairness definition, that means I want my predictor to predict equal probability of having fever for, let's say, if A is gender, male and female, right? So I want my predictor to predict a male has an equal probability of having fever as a female. This may sound okay to you at the moment, but what about if, right? I'm not building. I don't like fever, and fear is not cool, right? What about I want to build a predictor for heart attack, right? In that case, do I still want my predictor to predict equal probability of having a heart attack for men and women? Right, you can start see things get a little bit sketchy here. Then, right, if I go to an even more extreme case, what if my outcome is breast cancer, right? Does a predictor predict equal probability of having breast cancer for men and women? Is a reasonable assessment of fairness? So the three examples that I just gave you, fundamentally, they differ in the base rate of the outcome, or in other words, the proportion of actual positive outcomes. And that is one of the main criticism of this definition, is that it overlooked the potential fundamental differences in the outcome across the different groups. And to overcome that problem, that leads us to the second definition, equalized odds. So instead of pursuing marginal independence of the two, we're now saying that if our prediction and the protected attribute are conditionally independent given the true outcome, then our predictor is still fair according to equalized odds. So what this, it will be easier to understand when for a binary outcome. Why? So for example, here I write down this definition, this conditional independence under a binary outcome setting can be written as this. So what this is saying, that if we still use the heart attack as an example, so that means given condition on whether some condition on a patient has a heart attack, whether he's male or female, my prediction is the same, right? Given that this patient, so in other words, right, in the in the patient who have heart attack, this constraint is equivalent to the equalized true positive rates across protected groups. And when this equals 0, this constraint equalized the false positive rate should be equal across the protected groups. So basically this takes into account this allows the base rate of the outcome to be different across the racial groups or the protected groups. And to extend this to a continuous outcome, then the RMSE actually coincide with the definition of equalized odds. So this definition punishes models that perform well only on the majority. In other words, if the outcome is much more frequent in one of the protected group, then to satisfy equalized odds, the model cannot just predict the majority group, all people from the majority group has the outcome. It still needs to, because in that way you wouldn't have the same true positive rate or true negative rate across the two racial groups. So far, those two definitions apply to, predictive models. If you have a prediction model, and you have some sensitive attribute that you want to assess fairness on, what can you do? There's some also other definitions that is under a causal framework. So the first one is called equal opportunity. So using college admission as an example, and the sensitive attribute in this case is gender, then what is a fair algorithm for deciding on whether admitting an applicant to college or not? Right, so to satisfy EO, what this equation means is that, let's ask this question: what would the algorithm decide for this applicant if the applicant achieved the same SAT score, but she was a male, right? So for a female applicant, what would the algorithm decide if she achieved the same SAT score, but were a male? If that does not change our decision, then the algorithm satisfies equal opportunity. But we can go one step further, right? From our data, so we observed that female students have on average lower SAT score than their students who are male. So we can hypothesize that if someone were belong to a different gender group, he or she could have a different SAT score due to maybe the access to materials, due to how good they are at following teachers' orders, how good they're at submitting their homeworks on time. But there could be many hypotheses. So if someone were in a different gender group, he or she could have a potentially different SAT score. So what this counterfactual fairness definition says is that only condition on the observed SAT score is not enough, because if someone were from a different gender group, that could have a causal impact on the SAT scores the students could have got, and that will affect his or her college admission. So if we intervene on the protected attribute, we need to condition on the potential outcome of basically all the variables in the causal pathway between the protected attribute and the outcome. And that is the main difference. As if I go back one slide, you'll see that's the main difference between equal opportunity that I condition on what currently observed versus here conditioning on what potentially could have been if under the impact of intervention on gender. So those are the 4 definitions. And for this GFR prediction problem, we decided that because it is a prediction algorithm that only has 4 variables, the current clinical algorithm only has 4 variables. I don't believe that it tries to tell a causal story. So it's more of a prediction algorithm to me. And I think an equalized odds assessment would be a good metric to use here. I can go into the other definitions further in the second part of this talk if we have time. But let's go back to this GFR case study, right? So our goal is to evaluate the accuracy and fairness of GFR prediction algorithms in response to the use of race. And we use the CMC EHR data. So here's my cohort definition and characterization. So I first extract patients based on the availability of some of the variables in the database. Urine creatinine level, this is 24-hour creatinine from urine in order to calculate the true GFR for patients, and also serum creatinine, body surface area, and age, as those variables are necessary, are included in the CKD epi equation. And here's showing the age distribution, gender distribution, and race distribution of the cohort. So mainly for the race distribution, patients whose race is coded as white and patient whose race is coded as Black or African American accounts for the majority. So only those 2 are included in downstream analysis. So first of all, right, for the CKD epi equation, we want to know whether removing race has an impact. So that is our first algorithm, and we use it to estimate the GFR with and without the race modifier. The second model is a linear regression. It's developed using the same 4 variables, but in a linear form, and we developed the model using our data and evaluate on our data. We do this step, we have this model here is in order to better compare with another model that we also developed using our own data. And that is a lasso regression with all variables available in the database. And we train this model with all variables with or without the race variable. So in this case, it's binary patient who's white or who's Black or African American, subject to the regularization. So to evaluate the models, right, we evaluate based on model performance and also fairness. So for model performance, how well a prediction model is at predicting the outcome, given that GFR is more of a continuous measure, we use RMSE. And we show the RMSE for all patients, for patients whose race is coded as Black, and for patient whose race is coded as white. We specifically compute RMSE for Black patients and white patients because that allows us to validate and equalize the odds. Because if they have if the RMSE for patients, Black patients and white patients are the same, then that satisfies the definition of equalize the odds. Right, so here are the results, and I'll walk you through one by one. So on the left, I have the three types of algorithms, although with and without race. Each of them have two variations, so there are total 6. And for each algorithm, there are 3 RMSE for the entire cohort, for Black patients and for white patients. So first, when you look across the board, you can see that the prediction error for Black patients was higher than that for white patients across all the methods, right? So that's number 1. And second, removing race did not always lower the prediction error for Black patients. In the example of the CKD-EPI equation, if I remove the race variable, it actually leads to a higher error of prediction for Black patients. And it's kind of the opposite here, not much change when you include all variables in the lasso regression. So it's not clear, but it does not always lower the prediction error. And so this too tells us all the models actually violates equalize the odds fairness, because none of them give us the same RMSE across the 2 racial groups. But are there some better than others? Right, so let's take a look. So for equalize the odds, what we're really asking is, right, how far apart are my error for one group compared to the error for the other group? So removing race, we can see that this leads to actually an increase in the difference. This is a slight decrease. This is a slight increase in the difference. So when race was removed for an algorithm, it did not decrease the difference in error between the 2 groups. In other words, it does not make you closer to equalize the odds by just removing race from your predictor set. All right, so those are all interesting findings, but some were maybe frustrating. So here are maybe some good news, is that for the model that include all covariates, the lasso regression, it produced the smallest RMSE compared to the previous 2 models. So, and this means a better prediction, not only just for Black patients, but also for white patients. And this is the same whether you use race as a variable or you do not use as a predictor. The RMSE stays low. And furthermore, if we look at the difference again, the difference between the RMSE between the 2 racial groups also achieve this, we achieve the smallest difference with lasso regression compared to the other two models. So in other words, even though none of them really satisfies equalized odds, seems, but at least, of course, there's standard deviation. If there were a statistical test that can more rigorously test, that would be great. But by just looking at the two numbers and compute the difference, this does not seems to be satisfying equalized odds criteria. So I just walk you through all the 5 points, but here's a summary of them. There's definitely some limitations to the study, just like all other studies do. This data only represents patients seeking care at one hospital. Patients with missing race, age, and sex and 24-hour urine creatinine were not included. We only analyzed 2 racial groups due to limited data for other racial groups. And also the lack of genetic data and social determinants of health data in the EHR limits our ability to fully understand the role of race in estimating GFR. So here's the conclusions from the case study. We did not observe a significant difference in GFR prediction error after including or excluding race among all 3 methods tested. The error for patients coded as Black was higher compared to those coded as white, regardless of the inclusion of race as a variable. And more variables other than those used in current clinical algorithms help achieve more accurate GFR prediction, also leads to difference in prediction error across racial groups. In other words, according to the equalized odds criteria, that could mean potentially more fair yeah, I guess I'll here see if there's any questions that people want to ask regarding the study, or if not, I will move into the second part.
I have a question, sorry.
Oh, yeah, go ahead.
I have a couple of questions. Cool. First of all, thanks for sharing those results. So the first question I had is why do you think that the model is performing worse for Black than white patients? Is it because there's a bias in the data set that just seems to be that, you're not accurate, for example, that clinicians are not accurately recording all the data for Black patients that they are for white patients, so the model just can't learn very well? Or is it more to do with the fact that the number of white patients vastly outnumbers the number of Black patients in the model, so the model can, tricks itself into thinking that it's doing a very good job just by optimizing for white patients? Do you know which of those reasons, or if it's another reason that's kind of causing the bias?
Yeah, sure, very good question. So in this case, I don't think the model is optimizing for, so we do have a data imbalance, but I don't think the model just optimized for white patients and total disregard, although, being a minority in a prediction model, that could mean if you look at the RMSE, so the model optimized the overall RMSE and everyone contributed equally. So if the minority group, just due to the proportion of them in the data, could make them vulnerable to the predictions. But I think it also may have something to do with the variable race itself, how accurate it is in representing a lot of information. Maybe it's biological, maybe it's social and economical. There seems just more heterogeneity in even the true GFR when you look at the true GFR distribution across patients who are Black, and compared to that to patients who are white patients. So what is the cause of that heterogeneity? Is that due to our data, like the bias of data, like, patients with a wide range of GFR comes to our hospital versus the white patients who come to the hospital, I guess it's unclear, and that needs to be better understood.
Okay, thank you.
But can I quickly follow up on this also? I don't know if you've showed this, but the data set that you have, what's the proportion, the proportion of data points for white versus black patients in that data set? Is it possible that you just have a much fewer data points? You may have talked about it, but I missed it.
Yes, so I have the slide up on the screen again. So for the race distribution, the black patients about a quarter,
right? Okay,
maybe a third of.
So that could be another source of your error, right? So this is just a very limited data set for that.
Yes.
That's
so I didn't show exactly. So what I didn't show here is that. So for all the models I have showed you, they are all trained on the entire cohort, but I calculate the error separately for each group. So what I did try is that I trained a model only on data from white patients, or a model trained only on data from black patients. So for that model, those two models, the error for black patients are still higher than the error for white patients. And in that case, there's no competing of the two groups in determining the total error. So I think whether I don't have that information right now at the moment, but each time when how I get the RMSE and the standard deviation is through bootstrapping. So each time the data set would due to bootstrap can look a little bit differently. And for stochastic algorithm like lasso regression, it could potentially pick up different variables. But I agree with you, maybe if there's a consistent pattern on the variables that the model picked, and that can tell us more about how the model makes the decision. And again, I think I didn't show the lasso regression with 10,000 variables as a potential alternative to the CKD epi. I agree with you that a model with 4 variables has an advantage when someone needs to calculate a number at the point of care. I think it's more as a way showing the lasso regression with more variables is more of a way showing there are more information that maybe should be taken into account to understand the problem better, from maybe a pure prediction to a more causal understanding of the reasons behind. Yeah, all good questions. Thank you. So the second part is more like a discussion or some of the ideas that I have throughout working on the GFR project. And it's still ideas that are under development. And but I just want to take this opportunity to share with you and get some feedback. So we discussed the different definitions and sort of I sort of gave examples on maybe one is better than the other, and we went with equalize the odds for the GFR problem because we think it's a prediction problem. But what if you have a causal problem? Or in other words, I think initially when we asked this question whether race should be included in GFR prediction, it could be interpreted as a causal problem. But how you decide what is the question to ask, it depends on maybe the data you have, it depends on the algorithm that you want to design, the application of it. So it is very, like all the things kind of interact with each other. But how do we approach an algorithmic fairness problem? Okay. So I recall if you read Pearl's book, The Book of Why, you probably would remember this letter of causation that Pearl proposed in this book, that he divided the world into he divided not the world, but the machine learning, all the machine learning models or statistical models, all types of models that we developed into 3 hands of a letter. It's seeing, doing, imagining, and you can also call it association, intervention, and counterfactuals. So the first hand of the letter, association, that is when you have variables and you have an outcome and you ask this question, how are the variables related? So, and when you're in the intervention world, you kind of ask what is the effect of some intervention on the outcome, and then you go to the third level and asking, given that I have seen all that have happened, what would have happened if something changed? So I feel like if we can categorize all the models that we built to this point into the 3 buckets, then when we are assessing fairness of algorithms, it probably do. And I think that helps a lot when I try to, when I see a new definition of fairness and try to think about, which hand of the letter it belongs to. And so I give some example here. It's the same definitions that I just talked about before, but now let's see which part of the letter it belongs to. So for association, right, the first association, demographic parity and equalize the odds can all goes to this level. And some of the example questions that you may ask, I gave some before, but here more. Right? What if you're asking, does the algorithm have an equal opportunity of prescribing aspirin to men and women? Right? Or does the algorithm predict, the example I gave, equal probability of having fever between men and women? That is, you are asking a question to assess demographic parity. And for equalize the odds, that ask, for example, a question that you can use equalize the odds would be, does the algorithm predict that men and women have equal probability of surviving an ICU stay condition when they survived? And the second level, so in the first hand of the letter, you don't need a causal framework. You don't need a causal graph or any causal knowledge. You just need a bucket of predictors and an outcome interest, and you try to build a relationship and see, and you can assess fairness using demographic parity or equalize the odds. Starting from the second level, it is under a causal framework. So in that case, the 2 definitions we discussed, equal opportunity and counterfactual fairness, I think all belongs to this level. And I gave more examples of the questions that could be asked or could be assessed with those definitions. So I won't read it, but I think it's fun when I come up with these examples. And really, so for the third level, the counterfactuals, I think not only I didn't see much of modeling really on this level, but also there seems, or my literature review hasn't got there yet. So I don't know what a good definition would be that belongs to this level, but that's something for my future study. So those are the, I think, the 3 ways of categorize the different definitions. And I have a feeling that you're more likely to encounter a causal problem than not. So how to better understand how mechanistically how things work, it is essentially a causal problem. So how to approach a causal fairness problem? I think from my experience, I've been repeating this 4 steps over and over again. So, and I think it includes basically draw a causal graph, write down the goal, and assess identifiability, and build a model for estimation. So the step 1, draw a causal graph. A causal graph encodes assumptions of the data generating process. So for example, thinking just, this very abstract causal graph, let's say we have some outcome, health outcome of interest, and that depends on, maybe your genes, some social determinants of health, and those are affected by your race and some other health depending variables that are not affected by race. So by writing this causal graph, what I just described are the assumptions that I made for this study. So what does it mean write down the second step, write down the goal? Right now I have some of the variables. I can assume that's how data are generated with these errors that connects those dots. Now I can write down the goal. The goal is basically the effect that you want to estimate. For example, the goal can be to estimate the effect of race on health, and using Pearl's due notation, that means I want to understand the effect of race on health conditioned on other variables, like others. Or I can understand the effect of gene on health. In that case, the outcome is health, and I want to intervene on gene, right? If someone had a different SNP, what would his outcome be conditioned on race? So that's right. And so you write down the goal. And to assess, the third step is to assess identifiability. So for any causal estimate, can you estimate it based on a causal graph? So, and that I think we call the D separation or the backdoor assessment. If you are familiar with those terms in causal literature. If not, basically we're just saying if there's a backdoor, if there's any other way that information from your intervention can affect your outcome other than this error here. So if there's no other way, then this causal estimate is identifiable. If there's any other backdoor that you are not able to block, then your estimate is not identifiable. And right, for the GFR project, when it comes to medicine, it's always more than just a few variables, always much more complicated. So I've drawn the different graphs to understand, if we were asked a different causal question, that, to better understand the role that race play in GFR prediction, what this graph would be and what can we do. So yeah, that's basically what I've been, or what I will be working on in the future. But just to conclude today's talk, I showed a case study where we assessed the impact of race on accuracy and fairness of various GFR prediction algorithms. And the letter of fairness maybe can be potentially useful framework for designing algorithmically fair clinical models. With that, I'd like to thank my 2 advisors, George and Dave, for their guidance, and my colleagues, Lauren, Yan, Harry, and Anna, for the very helpful discussions. Yeah, and that concludes my talk today. Feel free to ask questions.
Yeah, thank you, Linying, for the great talk. I think we're open. Yeah, we have like around 10 minutes for questions. Yeah, I saw Ahmed. Yeah, go ahead.
Slide should I put?
Oh, can anyone hear me? Or am I still muted?
Yes.
There we
Yeah,
go.
we can hear you now.
I was muted earlier and I was talking and I realized I was just talking into the air. For your first model thing, I think you were talking about like what particular variables were important, but just because I might have missed it, what exactly were all of the variables that you used for the like the third model?
So that's demographics, except race and ethnicity, measurement, diagnosis. It's like the default covariance setting in Odyssey package. So diagnosis, measurement, demographic with or without race, and no ethnicity. What else? I think. What are the things in
Is it just
Elma?
like the condition occurrence table and like the?
Yeah.
I see.
Yes,
Okay.
yes.
I did something like somewhat vaguely, not super similar, but I did it for like gender, and I did like entry into like I didn't predict like a biomarker, but I predicted like whether someone had Crohn's disease, and I just blinded them to the gender. I just like knocked out that column, for instance, and then I just put in all of their condition occurrences, and I generally found that something in the condition occurrence data seems to imply that there is some gender information somewhere in the condition codes themselves. And I dropped codes that were like unique to men or women, a single gender. I just put codes that were common across both. So something in there probably has gender information. I don't know about race, but there could be some information leakage. I guess that's just my comment.
Yeah, definitely. You're definitely right. So there's literature on proxy variables. So, and the example you gave are, like a case of proxy variables, right? Some may be. So what that means is that those variables, although they are not labeled as race, or gender, it carries information. For example, that how gender or race impact the clinical care, and that can be reflected in the diagnosis code, or what lab tests are ordered. So yes, and that's why I don't think, for example, the model with more variables are right. The model, so that the model without race as a variable can still have information about race from other variables. One potential approach that we could do is to there's some representation learning that called disentanglement, that you basically project, I think, all the variables to the variable race and find the perpendicular projection. So that way, right, if you
Least related
if that's
concepts.
something that, yes.
I wonder if you did that, how many of them would be independent of race, or like how far away the variables would be. And a separate question that's like kind of also not super related to this one was, you were using like root mean squared error for equalized odds. Could you explain, like, my understanding of equalized odds is it's like equality and like true positive rates. So could you explain a little bit of how you got from true positive rates to root mean squared error differences?
Sure. Let me see. Right, so this is equalized odds, and because it has the words odds there, it feels just more natural that way, for binary outcome. But what really this, right? You condition on the true outcome. So for RMSE, I think this condition translates to the difference, the error, because ultimately for equalized odds, you're asking how far my prediction is from the truth. When it is binary, then you can write it as the two equalities, when y equals 1, y equals 0. But for continuous variable, then you're basically comparing each prediction to its truth, how far away that is. So this condition, I think this condition is taken into account by calculating the squared difference.
Makes sense. Thanks.
Mhm.
I guess I'll jump in here if no one else has questions. In the analogy you were making to the ladder of causation, I think I missed the distinction you were making between like the second and third rungs. So could you explain that last bit again?
Sure.
That'd be great. Yeah.
All right. Many slides away. Sorry for flipping it through. Yeah. So the difference between, right, so let's talk about the ladder of causation. The ladder of causation, the second ladder, I think we all understand, is when you have an intervention. Maybe I'll go with the second. When you have an intervention and outcome, you ask this probability, right? What's the probability of the outcome given due the variable that you're interested in? And then you condition on all the other predictors that allows you to, right, or the variables that block backdoor path. But for the counterfactuals level, what Pearl actually interested in is the probability of why the outcome under, I think I will use this notation here. It is the potential outcome under the intervention, given not only just the predictors for the intervention, but also the observed outcome. So the example that he gave us that if you know that someone used a lighter and there's a fire, what would the counterfactual be if someone did not use the lighter, you know, whether there would be a fire. So I think the essential difference is that you're not only conditioning on those variables that allows your causal quantity to be identifiable, but you're also conditioning on, you know, what happened in the actual world. Mm-hmm. So, and the word counterfactual, I think, is being abused because counterfactual fairness actually does not, I think my understanding is that it still belongs to the second world, because you are still doing backdoor adjustment and asking the backdoor adjustment, and you intervene on a variable and you're conditioning on the potential outcomes of all the variables that could be impacted by your intervention, but you did not conditioning on what is observed in the actual world. I don't know if that is clear, but yeah, happy to discuss it more offline.
Yep, I think that's clear. Thanks.
Yeah, but how this would translate to, you know, what definitions would fit this? Yeah, I'm still exploring.
Is there any other questions? Okay. Actually, I have maybe a very high level question. Help me understand the motivation of this study. Is like, if your model considering race, including race as a predictor, and it achieves like a very high level of accuracy, why would you want to like remove it and to assess fairness here? Is that because, for, you know, in reality, when you apply this predictor algorithm, if a patient has, we don't have the race information, we want to see if the algorithm like make the correct prediction, or it consistently biased towards some race. Is that I'm not sure that's relevant to this, but I was curious.
Yeah,
like,
yeah,
what's
it's definitely.
yeah. Yeah, thank you.
Yeah, so That's a very good question, right? So when we are talking about race, what are we really talking about? And I think the move from having race in the CKD-EPI equation to now some institutions start dropping that variable from the CKD-EPI equation is a response to the concerns about algorithmic fairness. But I don't know if that is the best approach, or if that approach, if at all, solve the problem of the disparities in healthcare. I think that there's much more beyond just including or not including certain variables. Well, in other words, I guess if this model is perfect, right, perfectly at predict something, GFR, for all the racial groups, all genders, and all age groups, then maybe people would not even asking this question to begin with. It's because that I guess for a very long time, people who are building these models did not fully understand the impact of their model on the majority versus minority, how model make choices, and that start to make people concerned about what do you really put into the models. And I think that triggers the question about whether race should be used. But I think my point of presentation is to show that it's beyond what should be included. There should be more causal knowledge underneath. There should be more effort and resources put in to understand the mechanisms about how race or gender affected health.
I think it makes sense. Okay, we're just on time for this. Thank you again for the great talk, and I think we are adjourned here. I'll see you guys next week, right? Okay. Happy Thanksgiving. Yeah.
Happy Thanksgiving.
Yeah.
Thanks.